With light and refraction, something interesting can occur called total internal reflection. When the light is starting out in the substance of the higher index of refraction and it's incident at a large enough angle, then it will bend so far away from the normal that it ends up not leaving the substance but instead staying in the substance, which then would be called a reflection. Let's consider this problem-solving application. So you have a rock called ulexite, which is sometimes referred to as TV rock, has an index of refraction of 1.496. And you have in part A, the rock is surrounded by air. Calculate the critical angle. So if we're going to have total internal reflection, then the light has to start internal. So that means it has to start in the ulexite and be incident on air. So then in Snell's law, N1 sine theta I equals N2 sine theta R. We're starting with ulexite. It's going to be total internal reflection of the light in the ulexite. Okay, and what we're calculating is the critical angle where theta R is 90 degrees. So then when we plug in, this would be 1.496 sine this incident angle would become theta C. N2 would be air, that's a constant index of refraction, 1.000293. And then sine of 90 degrees, and the sine of 90 degrees is 1. So then when we solve down for theta C, we get a value of 41.96 degrees, okay, which means if the light is incident at this angle, we get a refraction of 90 degrees. So this is the largest angle. Any angle smaller than this, and we will get a normal refraction. When the light is incident at any angle greater than this, we will get a total internal reflection. Now, in part B. Now, if the rock was submerged in water, would the light need to start in ulexite or water to experience total internal reflection? Ulexite is a 1.486 or 496, and water has an index of refraction of 1.333. Total internal reflection, the light has to start in the substance of the higher index of refraction. That would be ulexite. So then, on the first part, light starts in the ulexite. Now, the second part. Would the critical angle increase, decrease, or remain the same compared to when the ulexite was in the air? Well, if we consider index of refraction, index of refraction describes how light is going to refract, and the higher the index of refraction, the more the light slows down, and the more the light slows down, the more it refracts. So then our difference between air and ulexite was significant, more significant than our difference in the index of refraction of water and ulexite. So what that means is there's going to be less tendency to bend when going between water and ulexite, okay? And if there's less tendency to bend, there's going to be less likelihood of total internal reflection. Less likelihood of total internal reflection, then our angle is going to have to be greater to be able to get that total internal reflection. So then we expect that theta C would be greater when the light goes from ulexite to water. If indeed we plug in our numbers, replacing the index of refraction here by water, and we calculate that theta C that we get is 63 degrees. So it is indeed larger than the 41.96 that we got for ulexite to air. Ponder physics.